Have you ever looked at the vast universe and wondered why things are the way they are? Why isn't everything perfectly identical, perfectly balanced, perfectly symmetrical? It feels like everything around us, from the tiniest atom to the biggest galaxy, has unique properties. But what if I told you that at its most fundamental level, the universe started out much more symmetrical than it is today? And that many of the distinct features we see, including the very massive particles and the forces that govern them, came into existence through a fascinating process called spontaneous symmetry breaking? Let's unravel this mind-bending idea. Imagine a perfectly round, smooth dome, with a ball placed precisely at its very peak. From a physics perspective, this setup is incredibly symmetrical. The ball could roll down in literally any direction. North, south, east, west, or anywhere in between. All directions are equally probable. This is a state of high symmetry. The underlying laws, gravity pulling the ball down, don't favor any particular direction. But what happens if there's a tiny, imperceptible nudge? Perhaps a microscopic vibration, or even a quantum fluctuation. The ball will inevitably start to roll down, and once it begins, it must pick a specific direction. It can't roll down in all directions at once. Even though the dome itself is still symmetrical, the state of the ball is no longer symmetrical. This is spontaneous symmetry breaking in action. The laws governing the system are symmetrical, but the system's actual state is not. Another simple analogy. Imagine a perfectly sharp pencil balanced on its tip. The laws of physics say it could fall in any direction around its axis. It's rotationally symmetrical. But the moment it inevitably topples, it picks one specific direction. The rotational symmetry is broken. This fundamental concept isn't just about balls and pencils. It's a profound principle that explains some of the most critical phenomena in our universe. Let's look at a real-world example you might even have in your home. A magnet. Inside a piece of iron, there are countless tiny magnetic regions, each acting like a tiny compass needle. At high temperatures, these tiny magnets point in random directions. The overall magnetic field of the iron piece is zero. It's symmetrical, with no preferred direction. But cool, that iron down below a certain critical temperature. And something amazing happens. The tiny magnetic regions suddenly snap into alignment, all pointing in the same direction. They spontaneously break the rotational symmetry of their random orientations. Now, you have a permanent magnet with a distinct north and south pole. The underlying physics allows for any direction, but the system chose one. But the most profound example of spontaneous symmetry breaking comes from the very fabric of our universe, explaining why particles have mass. In the earliest moments after the Big Bang, the universe was incredibly hot and dense. Scientists believe that all fundamental particles were initially massless. The fundamental laws of physics at that energy level treated all particles equally, without distinguishing between them based on mass. This was a state of beautiful, perfect symmetry. No particle had a preferred heavy or light quality. But as the universe expanded and cooled, a crucial phase transition occurred, much like water turning into ice. A mysterious, omnipresent field, now known as the Higgs field, condensed throughout space. Before this condensation, the Higgs field had a symmetrical, zero-energy state, like the ball perfectly balanced on the dome's peak. But after cooling, the field spontaneously settled into a new, lower-energy state, like the ball rolling down and settling into a valley. This act of the Higgs field choosing a particular non-zero value for its energy density, breaking its own symmetry, had colossal consequences. Now, as particles travel through the universe, they interact with this Higgs field. Some particles, like photons, don't interact with it at all, or only minimally. they remain massless and zip around at the speed of light. But others, like electrons and quarks, which make up protons and neutrons, interact strongly with the Higgs field. They experience a kind of drag. This interaction is what we perceive as mass. The more a particle interacts with the Higgs field, the more massive it is. So, the very existence of mass, which allows for atoms, stars, planets, and even us, is a direct consequence of this spontaneous symmetry-breaking event in the early universe. From a simple magnet to the fundamental particles that make up everything, spontaneous symmetry breaking is a powerful, elegant principle. It tells us that the rich complexity and specific properties of our universe didn't necessarily come from intrinsically asymmetrical laws, but from symmetrical laws whose potential states chose a specific path. It's a reminder that even tiny, random fluctuations can lead to profound, universe-altering consequences, shaping reality as we know it. So, next time you pick up a magnet, or simply ponder your own existence, remember the incredible journey of symmetry breaking that made it all possible. Keep exploring, keep questioning, and keep discovering the hidden magic of science.